Today we'll start chapter 11, section 11.1 on sequences. A sequence is a list of numbers in a definite order, and notations for a sequence include the following: a sub 1, comma, a sub 2, and so on. The nth term in the sequence is denoted a sub n. You could put those in set brackets, a sub 1, comma, a sub 2, and so on. You can put set bracket a sub n, and if you want to be more explicit, the sequence of the terms a sub n as n ranges from 1 to infinity. We'll look at some examples of sequences, and just note that in a sequence, n doesn't have to start at 1. We often do start at n equals 1, but we don't have to. Okay, this sequence, the sequence of numbers 1, 4, 9, 16, and so on, it appears to consist of the squares of the natural numbers in ascending order. So if that's what that sequence is, this can be represented this way. It's the sequence of the terms n to the second, where n ranges from 1 to infinity. This sequence, 2, negative 2, 2, negative 2, and so on, if it follows that pattern, we call that an alternating sequence. But we can write it as 2 times the number negative 1 to the n plus 1, as n ranges from 1 to infinity. So here's the sequence. See if you can find a formula for the nth term of this sequence. So we'll say that a sub 1 is 2/3. A sub 2 is 3/9. A sub 3 is 4/27. So what's the nth term? Did you come up with a nth term?
Is there n plus 1 over 3n?
Okay, yeah, so in the numerator, the first numerator is 2, and then after that, the numerators increase by 1. So when n equals 1, the numerator is 2. When n equals 2, the numerator is 3. So the numerator is n plus 1. And in the denominator, we have powers of 3. 3 to the first in the first denominator, then 3 to the second, 3 to the third. So for the nth term, the denominator is 3 to the nth. Hey, for the next one, this one is not really hard, but what's a formula for the nth term of this one? So we have a sub 1 is 6 over 5. A sub 2 is 26 over 25. A sub 3 is 126 over 125, and so on. So the nth term looks like we need a numerator and a denominator. So somebody online, what do you get for the nth term in that sequence? Did you get it already?
Is it 5 to the n plus 1 or 5 to the n?
Okay. Yeah, the numerator is always just one more than the denominator. But the denominator consists of powers of 5. So 5 to the first, 5 to the second, 5 to the third. So the nth term, 5 to the nth plus 1 over 5 to the nth. Okay, moving on. Some sequences don't have a formula for the nth term. An example, if a sub n is the nth decimal place of the number pi, then the first few terms of that sequence, a sub n, are 1, 4, 1, 5, 9, and so on. So the number pi is irrational. That means the decimal portion is non-repeating and non-terminating. Okay, some sequences may be defined recursively. That means that future terms are defined in terms of original terms. So here's an example. Suppose a sub 1 is equal to 5, and then the a sub n plus 1 term is equal to a sub n squared minus 2 times a sub n for n greater than or equal to 1. Okay, so the second term, a sub 2, is defined in terms of the a sub 1. So a sub 2 is a sub 1 squared minus 2 times a sub 1. So since a sub 1 is 5, a sub 2 is 5 to the second minus 2 times 5. Then the third term, a sub 3, is defined in terms of a sub 2. It's a sub 2 squared minus 2 times a sub 2, or 15 squared minus 2 times 15, which simplifies to 195, and so on. Okay, the next paragraph. Some sequences can be pictured by plotting points on a number line or in a two-dimensional plane. So in the textbook, there are examples of that on page 695, figures 1 and 2. So you can look at that. Okay, that brings us to a definition. First definition on page 696 of the textbook. A sequence of terms a sub n has the limit capital L, a finite number, if the terms a sub n can be made arbitrarily close to capital L for sufficiently large n. The notation, if the limit of the sequence a sub n as n goes to infinity equals L, where L is a finite number, this is one notation for the limit of a sequence. A more compact way is to say that the a sub n terms approach capital L as n approaches infinity. So both of those notations mean the same thing. Okay, then the next one, if the limit as n approaches infinity of a sub n exists as a finite number, then the terminology for that is to say that the sequence a sub n converges, or that the sequence is convergent. Otherwise, the sequence diverges, or it's just divergent. Okay, on the next page, here we have another definition. The sequence a sub n has the limit capital L, a finite number, if for every epsilon greater than 0, there is a corresponding integer capital N such that n greater than lowercase n greater than capital N, then the absolute value of a sub n minus L is less than infinity. So you had some exposure to that in Calculus 1, probably, if not with sequences, with functions. So recall from Calculus 1 the meaning of the limit of f of x as x approaches infinity equals L, where x is a real number in the domain of f. So the following is a useful theorem that connects the limit of a function of x to a corresponding limit of a sequence, which is a function of n. So just to reiterate that, if we have a sub n term from a sequence, then we can define that as f of n for natural numbers n. And so a sequence of a sub n terms could be denoted as the sequence of f of n terms. Okay, so Theorem 3, if the limit of f of x as x approaches infinity is equal to capital L, a finite number, and f of n equals a sub n, where n, whenever n is a integer, then the limit of the sequence a sub n as n approaches infinity is also equal to L. Another note from Calculus 1. In Calculus 1, we learned that if r is greater than 0, Then the limit as x approaches infinity of 1 over x to the r is equal to 0. So by applying Theorem 3 to sequences, if we have a sequence 1 over n to the r, then that sequence converges to 0, provided that r is greater than 0. Okay, so that is what the equation 4 on page 697 says. The limit of 1 over n to the r as n approaches infinity, this limit is equal to 0 if r is greater than 0. Okay, now let -1 be less than r, which is less than or equal to 1. Then the limit of r to the x as x approaches infinity is equal to 0 if -1 is less than r, which is less than 1. And the limit of r to the x as x approaches infinity is equal to 1 for r equal to 1. By Theorem 3, the sequence r to the n converges to 0 if the number r is strictly between -1 and 1. But the sequence r to the n converges to 1 if r is equal to 1. And the sequence r to the n diverges for all other values of r. Okay, the next definition, so you'll be familiar with this. The limit of the sequence a sub n as n approaches infinity equals infinity. This means that for every positive number capital M, there is an integer capital N such that if lowercase n is greater than capital N, then a sub n is greater than m. So if the limit of a sub n as n approaches infinity equals infinity, then the sequence of the a sub n terms diverges to infinity. Okay, on the next page, we have a list of the limit laws for sequences. So these limit laws for sequences are analogous to the limit laws of functions that you learned in Calculus 1. So in the setting, the sequences a sub n and b sub n they're both convergent sequences, and c is a constant. Okay, so if you have the limit of a sum a sub n plus b sub n as n approaches infinity, that's equal to the sum of two limits, the limit of the a sub n terms plus the limit of the b sub n terms as n approaches infinity. If you have a difference, a sub n minus b sub n, the limit of a sub n minus b sub n as n approaches infinity is equal to the difference of the limits. If you have a limit of c times a sub n as n approaches infinity, Well, you can factor c out of all of the terms and multiply the constant c times the limit of the a sub n terms as n approaches infinity. And then a reminder that if you take the limit of a constant, the limit is just the constant. So a constant is unaltered by whatever n does. If you have a limit of a product of terms, a sub n, the limit of a sub n times b sub n as n approaches infinity, this is equal to the product of the two limits. If you have the limit of a quotient, the limit of a sub n over b sub n as n approaches infinity, then this is equal to the limit of a sub n as n approaches infinity divided by the limit of b sub n as n approaches infinity. And this is provided that the limit in the denominator does not equal 0. And then finally, the limit of a sub n raised to the power p as n approaches infinity, this is equal to the limit of a sub n as n approaches infinity raised to the power p, if provided that p is greater than 0 and a sub n is greater than 0. So hopefully those limit laws all make sense. Okay, on the next page, we have the squeeze theorem for sequences. This is pretty simple to understand, but it's a very useful concept whenever we need it. This says we have three sequences. If a sub n is less than or equal to b sub n, which is less than or equal to c sub n, for all n greater than or equal to some integer n sub 0, and if the limit of a sub n as n approaches infinity equals the limit of c sub n as n approaches infinity, if both of those limits are equal to L, then the limit of the b sub n sequence as n approaches infinity is also equal to L. Okay, so that seems to make sense. Okay, now Theorem 6. If the limit of the absolute value of a sub n as n approaches infinity is equal to 0, then the limit of the sequence a sub n as n approaches infinity also equals 0. So we'll do a short proof of this. We're given what follows if in a conditional statement. The given information is that the limit of the absolute value of a sub n as n approaches infinity is equal to 0. Okay, that's the given information, and we're going to use it to prove that the limit of the sequence a sub n is also equal to 0. Okay, so what does this mean? Well, this means for every epsilon greater than 0, there is a natural number capital N such that lowercase n greater than capital N implies that the absolute value of a sub n minus 0 is less than epsilon. Okay, but the absolute value of a sub n minus 0 can be simplified. The absolute value of a sub n minus 0, that's just the absolute value of a sub n, but that's redundant. The absolute value of a sub n is just the absolute value of a sub n. And the absolute value of a sub n minus 0 is equal to the same value. And so this must also be less than epsilon. So this is what we would have to prove to show that the limit of a sub n as n approaches infinity equals 0. So this shows the conclusion, the limit as n approaches infinity of a sub n is also equal to 0. Okay, let's move on. Just remembering that this little fact, it seems pretty easy to understand, but it can be useful at times. Okay, Theorem 7, if the limit of a sequence a sub n as n approaches infinity is equal to a finite number L, and if the function f is continuous at L, then the limit of f of a sub n as n approaches infinity is equal to f of L. So remember that we can do this. I think you saw this in Calculus 1. This sort of thing. So if you have the limit of f of a sub n as n approaches infinity, well, this is equal to f of the limit of a sub n as n approaches infinity. So if that limit is equal to L, this is equal to f of L. Okay, so I'll give you some work. Find the limit of cosine of pi times n plus 1 over 2n as n approaches infinity. So take a minute or two and come up with the limit for that one. Getting close? Or are you already there? Okay, what do we do to start with? the limit of cosine of pi n plus 1 over 2n as n approaches infinity. What should I do first?
With regard to the cosine of the limit as n approaches infinity of pi n plus 1 over 2n.
Yeah, we'll do what the note above says to do. Cosine is just a function. So we can take the cosine of the limit as n approaches infinity of pi n plus 1 over 2n. And then we just need to know how to find the limit of pi n plus 1 over 2n. So we can do that on the side over here. The limit as n approaches infinity of pi n plus 1 over 2n. I suppose what I would do is I would simplify this this rational expression. Since there's just one term in the denominator, pi times n divided by 2n, the n's cancel, so we get pi over 2, and then plus 1 over 2 to the n. Pi over 2 is not affected by what n does, so pi over 2 is just pi over 2. But what about 1 over 2n? What happens to that as n approaches infinity? Goes to 0. So pi over 2 plus 0, because 1 over 2n goes to 0 as n goes to infinity. So this is equal to pi over 2. And so this is cosine of the limit, cosine of pi over 2. But cosine of pi over 2 is just 0. So 0 is a perfectly fine number. That's the limit of this function. Okay, now we'll move on to the next definition. A sequence of a sub n terms is called increasing for obvious reasons. If a sub 1 is less than a sub 2, which is less than a sub 3, and so on. It is called decreasing if a sub 1 is greater than a sub 2, which is greater than a sub 3, and so on. A sequence is called monotonic if it is either increasing or decreasing. So just note that a monotonic sequence can be one or the other. It can't be both. It's either increasing or it's decreasing. Okay, the next definition, a sequence of a sub n terms is bounded above if there is a number, capital M, such that a sub n is less than or equal to capital M for all n greater than or equal to 1. So in other words, if there is this is put an emphasis on finite number. If there's a finite number that all of the numbers in the sequence are less than or equal to, then the sequence is bounded above. The sequence is bounded below if there is a number lowercase m such that lowercase m is less than or equal to a sub n for all n greater than or equal to 1. It's possible for a sequence to be both bounded above and below, and if that's the case, the sequence is just referred to as a bounded sequence. Okay, the next page, the monotonic sequence theorem. Okay, the monotonic sequence theorem says every bounded monotonic sequence is convergent. So the proof is on page 702 of the textbook. Try reading it. I'll just explain a couple of things. The proof of Theorem 12, the monotonic sequence theorem, is based on the completeness axiom for the set of real numbers. So you'll probably remember from like a geometry class or something, an axiom is a statement that is accepted without proof. Okay, so the completeness axiom states that a non-empty set of real numbers that is bounded above has a least upper bound. And it also states that a non-empty set of real numbers that is bounded below has a greatest lower bound. So just to reiterate that, if a sequence is bounded above, then there's exactly one number that is the least of all upper bounds. Seems to make sense. The essence of the completeness axiom is that there is no gap in the real number line. So that is, every point on the real number line corresponds to a unique real number. Okay, one of the uses of the monotonic sequence theorem, even if we can't find what a monotonic sequence converges to, we can know that it is convergent if it's a bounded sequence. Okay, let's look at some examples where we find the limits. Find the limit of the following sequences. So the first one, the nth term, a sub n, is defined as 3n plus 5 over 6n minus 1. So what's the limit of a sub n as n approaches infinity? So in other words, what's the limit of 3n plus 5 over 6n minus 1? So with a little practice, you'll be able to look at that and know within 2 seconds what the limit is. Yeah, this is a rational expression in the variable n. So if we want to compute the limit as n approaches infinity, one technique is note the largest power of n in the denominator. So n to the first is the largest power of n in the denominator. So if we multiply this expression by 1 in the form 1 over n times 1 over n, then we can simplify that to an expression that might be easier to compute the limit of. So multiply by 1 over n over 1 over n. So another way to say that is multiply the numerator by 1 over n and multiply the denominator by 1 over n. So I'll just put that in here. So we have the limit as n approaches infinity. 3n times 1 over n is 3. 5 times 1 over n is 5 over n. And in the denominator, 6n times 1 over n is 6. And then minus 1 times 1 over n is minus 1 over n. And as n approaches infinity, 5 over n approaches 0, and so does 1 over n. And we're just left with 3 over 6, or 1/2. Okay, find the limit of the next sequence. A sub n is equal to 2n minus 1 over 4n to the second plus 1. And also with some practice, you'll be able to look at that and say what the limit is in 2 seconds or less. So we want to find the limit as n approaches infinity of 2n minus 1 over 4n to the second plus 1. What do we do this time? Okay, so in the denominator, the largest power of n is n to the second. So first note, this is just a rational expression in the variable n. So if we multiply by 1 in the form 1 over n to the second over 1 over n to the second, note that that's a perfectly fine thing to do because we're assuming n is going off to positive infinity, so we're not in danger of dividing by 0 or anything. We might be able to just get this into a more familiar setting. So we're multiplying 2n minus 1 over 4n squared plus 1 by 1. Okay, what's 2n times 1 over n squared? It's 2 over n. And then minus 1 times 1 over n squared is minus 1 over n squared. And in the denominator, 4n squared times 1 over n squared is 4. And plus 1 times 1 over n squared is plus 1 over n squared. And now we can calculate the limit. So in the numerator, as n goes to infinity, 2 over n goes to 0. And so does 1 over n squared. So the numerator goes to 0. That's perfectly fine for a numerator. And what's the limit of the denominator as n goes to infinity? Well, 4, the number 4 is unaffected by n. So we know that we have 4. And 1 over n squared goes to 0. 0 divided by 4 is just 0. So the limit of that is 0. Another possibility, using one of our theorems that we talked about, if we define a function f of x to be 2x minus 1 over 4x squared plus 1, and then compute the limit of that function f of x as x approaches infinity, we would get infinity divided by infinity. Remember what you do in Calculus 1? Use L'Hopital's rule, and then you can compute the limit that way. Okay, the next one, a sub n equals 3 to the 1 over n. We want to find the limit as n approaches infinity of 3 to the 1 over n. And so if we think of this as f of x equals 3 to the 1 over x, and then if we take the limit of 3 to the 1 over x as x approaches infinity, so I'm referring to a theorem that we talked about earlier. But let's just do this directly. If we have the limit of 3 to the 1 over n as n approaches infinity, then this is equal to 3 raised to the limit of 1 over n as n approaches infinity. And the limit of 1 over n as n approaches infinity is 0, so we get 3 to the 0, and 3 to the 0 is 1. Okay, so this sequence, the terms 3 to the 1 over n, those terms converge to 1. Okay, the next one, what are we going to do on this one? The terms are a sub n equals n to the 1 over n. So we want to find the limit as n approaches infinity of n to the 1 over n. So who knows what to do? Okay, well, we're assuming n is positive. So n just represents a positive integer, but more generally, for n greater than 0, n is equivalent or equal to e to the natural log of n, just using a property of exponents. Okay, so in this limit, we can replace n. So we're raising n to the 1 over n, but we're going to replace n with e to the natural log of n. And then we'll use another property of exponents. E raised to the exponent, the natural log of n, and if that's raised to the exponent 1 over n, then one property of exponents says I can multiply those two exponents. So I get e to the 1 over n times the natural log of n. And I'll just write it as e to the natural log of n over n. Okay, so E is just a number. It's approximately 2.71828. So what did we do earlier when we had the limit of 3 to the 1 over n? We wrote that as 3 to the limit of 1 over n. So we'll do that here. We have the limit of e to the natural log of n over n. So we'll write this as e to the limit as n approaches infinity of the natural log of n over n. If you let n go to infinity, what do we get? Or what's the limit of the natural log of n over n as n goes to infinity? Infinity over infinity. So we can apply L'Hopital's rule to the natural log of n over n. Okay, so the derivative of the natural log of n is 1 over n. We're taking the derivative with respect to n. And in the denominator, the derivative of n with respect to n is 1. And now we can compute the limit. The limit of 1 over n as n approaches infinity is 0. So we get e to the 0, which is 1. Okay, we're out of time for today. Go ahead and sign in for attendance.